Hey everybody, in the examples from last night we talked about how to calculate torques and find forces by using static equilibrium. So in a clip here, I'm going to leave the link in the description below. Why don't you watch this clip about the characters trying to tip a cow. So if we look at their setup there, this is how they model the cow. They're basically modeling the cow as a rectangle and taking the pivot location to be in this bottom left corner. So I want to set this up for you as well and see if what the math you see on this page kind of matches to what we would do in our problems. So here's the model of our cow, same rectangle. Forces on the cow are force of gravity acting straight down on the cow. We've got the pivot location to be in this bottom left corner, which means the normal force if the cow is going to start tipping, like if I tipped my iPad up on its side, only this bottom corner is where the force is acting for our normal force. The person that's applying the force is going to push off in that direction. So if I analyze this as putting forces on a lever arm, what I need is a lever arm. And here in the green arrow is what I'm going to say is the bar for that's now going to represent our cow. So when I look at analyzing my torques, I'm going to pivot down this bottom corner, which right off the bat tells me that I don't have to worry about the torque from the normal force because the normal force is acting at the pivot. The force of gravity here is acting at the center of the cow, and they give you some dimensions here. They say that the cow 64 centimeters lengthwise and 1.58 meters tall. So once I know those two dimensions there, I can use that to figure out distances along my lever arm. You should be able to figure out angles on the inside of the cow here and those distances, and the force of gravity is going to act at a distance of this far away from our pivot point. So find that distance and find that torque. Remember, using the components of gravity at that location. And if we look at the distance for that force of the push at the top of the cow, this is the distance that that force is acting at. So the two torques that are counteracting each other are the person's torque heading in the counterclockwise direction and the torque from the cow's weight that's going to go in the clockwise direction. Those two torques are going to cancel out. The only thing we don't know here, this force, the force that the person's going to put into lifting the cow. One other thing that you want to know is the mass of a cow is around 730 kilograms, or about 1,600 pounds. So using that information, go through your work, and I'll put an answer in the description below for the force that you would need to go and tip a cow. One other example I want to kind of look at real quick with you is this uniform log in problem 23 in the homework. The reason I want to look at it is because they give a lot of information about the length of the log, the width of the log, and the static coefficient with the log and the floor. Using this, they want you to find the tension and the angle that force is pulling that is vertical to the wall. So when we do a problem like this, one thing is I'll tell you is to not worry about the size of the log. Try to assume the log is just a thin rod with the forces acting where you would think they would. And the second thing is when we do that approximation, this may give you the force correctly or it might give you the angle correctly. And based off knowing the force or the angle, that should give you both answers 100%. But with WebAssign's tolerance, there is a slight issue with if you get one of these right, that's not guaranteed you get the other one correct. Go through and solve number 23. When you get to an answer for your angle or your force, if you think they are close and you've done everything you're supposed to, send me a message and I will tell you exactly how close they are. And I will give you, again, if you're within a few degrees, I'll give you one of those answers to allow you to get the second. So what we need to do is analyze the forces on that log. So I'm going to blow up that picture here. So the forces that I see on this log are simply 4 of them. I see the force of tension pulling up and to the right in that direction. I see the force of gravity acting straight down at the center of mass of the log. Over at the far end, the ground is providing a normal force straight up. And if I look in terms of my left, right, up, down forces, I see up and downs look pretty canceled, especially over with that torque. I've got an up piece of tension, but I also have a right piece of tension. And if I have a right piece of tension, that means I have to have a left force somewhere canceling this out. And that left force is going to come from the force of friction. So that's why they gave the static coefficient of friction when you did the setup. Now looking at those forces, remember we want to break up and sum up all our forces in the x direction and sum up all our forces in the y direction and make sure that those cancel out. So x forces seem pretty simple. Force of static friction backwards is going to equal the tension times the sine of the angle theta. And why is that sine of the angle theta? I'm going to take components to be in this direction for my tension. So there's my Tx and my Ty, and you can see that that now gives me the same angle as I have from the wall. Because our goal here is to find that angle of the wall and the tension in the line. In the y direction, my forces are T cosine plus the normal force. Those two are both up, and the force of gravity is down. So again, things that you do know is you know the mass of this log, you do know the coefficient of friction, and you know the length of the log. That's really what you want to focus on. So right now in forces we don't have a lot going on, so that means we have to look at torques. So when analyzing torques, we need a pivot point. And for me, the pivot point should be right there with that green dot. I'm going to pivot off of that tension. Why? Because the tension has two components to it, and I really don't want to mess with worrying about perpendicular components of that tension when the tension is definitely at an angle. So if I make the green dot my pivot again, now I can look at my torque from gravity, I can look at my torque from my normal force, and my torque from friction. Because each of these forces, you can draw perpendicular components with the angle that they give you from the bottom of the ground, from that 20 degrees. So drawing all of your torques, what I can write is a torque equation for each of those forces. So gravity is going to cause a negative torque with the component of its weight acting at the center of the log at 2 meters. The normal force is creating a torque all the way down at the end of the log, but that torque is in the positive direction. And if you look at friction and you break that into a component, friction is also creating a positive torque to make sure the log doesn't rotate. And the friction is causing a positive torque as well. And I'm going to write the friction equation as mu Fn sine 20 degrees 4 meters. So now you have a torque equation that's going to equal 0 because we don't want this thing to rotate. And you've got your two other force equations. Remember our goal here is to find the tension and the angle. But if you look at this torque equation, we have everything we need except for the normal force. And we can find the normal force, we can put that back up into our two force equations. So play around with that algebra, make sure you're balancing your forces and torques correctly, and when you think you get an answer, if you think you're following your math correctly, send me your response and I'll reply back. Good luck.